Chapter 7, Chapter 8, Chapter 9. Chapter 7, at least 3-hour lectures I'm planning. Chapter 8, rather short, but it's more a cookbook type, how they do, what they do for sharp qualification of equipment analysis and design, shipboard equipment. And Chapter 9 has some simple examples for computations and relevant to design. And then that's it. Then appendix is some basic criteria. Design and analysis criteria, I'm going to address on that. You may just read yourself. Then I'm going to, as I mentioned to you before, I'm going to go through some selective papers done in the past and maybe done here recently. That's what we're gonna do. That's about it. Okay. So one thing left is shipboard equipment. How to handle shipboard equipment. Why shipboard equipment relevant analysis and designs are important? Why? Because nowadays idea is not to sink the ship, but give a full damage on the weapon systems, for example, which is based on operated by the computer. Computer, inside the computer, you have a chip, computer chip. Right? Computer chips is like a brittle material, which can be easily damaged by high G, high acceleration level. All the chips are not flexible, but brittle material. When you really tap it very fast, it could give a damage. That's what the high G's you are talking about. So here, Chapter 7, sharp qualification of shipboard equipments by a design analysis method. So this is a beginning of dynamic design analysis method or approach. This is one of the methods. I don't say that this is the only method you could do for a sharp qualification of shipboard equipments. No, there could be all different way. But this is what Navy has been used for many years. Still they are using it. So I felt it's really worth it to deliver lectures on this. And especially if you're working on the Navy project or Navy ship or submarine, so this is what they are using it and worth it. Okay, but European Navy, they are not really using this particular method, but they have been using this method for a long time, but I don't know what they are using right now. So you can't just conduct a whole ship shock analysis and design all the time. So that's what this is. And the whole idea behind this chapter 7 is is this. You learn about the kickoff velocity. Kickoff velocity of ship, right? We have done kickoff velocity. You know how to compute the kickoff velocity, right? So you have a ship. It doesn't matter whether it's a ship or a submarine. Ship, when you say ship is in neutral buoyancy and floating on the free surface. And or you can draw the ship this way, or you can draw the ship by looking the other directions, right? And charge could be any place in the water. This could be, if this is that guy, this could be any place, any location. Then you know where the ship, what direction the ship is going to kick off. So usually is straight up. You know that. Regardless of location of explosive, ship kicks off. And when ship kicks off, if I draw the T versus usual response quantity of interest for ship shock testing or ship shock calculation is the velocity quantity. What was the reason? This work started in 1940, mid-1940, which means around 1945, which is right after Second World War. The research really begins at that time, and for the measurement sensors, they use velocity meters all the time. Velocity CT meters to measure. This is about this is about 1 inch, which is about 2.5 centimeters, and about that high, 6 inch maybe, 6 inch. 6 inch means 6 곱하기 2.5. 6 multiplied by 2.54 centimeters. But nowadays, the sensor manufacturer, they made all different size. So like if you involve on this PCB, they make a lot of different sensors for a long time. They make pressure, very good blast transducer. They make blast transducer very good quality. Blast transducer. This is really for pressure. Measure the pressure. And this velocity meter is rather simple. inside they have a mass and spring. Virtually that's about it. Then take that data out and check it out. They should have a velocity meter. But I'm just I just happen to know PCB, but there are other very good sensor manufacturer. And Devco is there. They could have this. They have also, but this you have to check it out. So, and Devco is very good, but expensive. And Devco is also very good sensor manufacturer. You compute the kickoff velocity. Kickoff velocity, how the signature would look like. At the time it goes bang, goes up to the max. Then after that, coming down, free fall. And usually, ship in terms of the displacement, the height, maximum height of the ship, it lift up, is very small. Don't think 1 foot, like maybe a quarter meters, 0.2, 0.3 meters, no. Very little it goes up, kicks up, then coming back down. So if I draw this, the kickoff velocity versus t, usually like this. For the surface ship, no, I'm just drawing very general. What I'm claiming here is triangular. In general, triangular shape of kickoff velocity. So if, as I wrote there, right there, if you look at the surface ship, it virtually goes straight up and decelerate something like this. It's almost straight up. If I draw if I approximately draw the shape in simple pattern, it's something like that, straight up and decelerate. Okay. Roughly, this is about negative 2g. Slope is concerned. And for submarine deep in the water, it's something like it could be like this. In other words, this is not close to zero. Well, you can, if you want, you can put this guy right here. Why? Depend on reference, where you put the reference zero. If you start to measure the data from the time the shock wave hit the target, then this could be zero. But if you set the detonation time as reference zero, right? This period from here to here, nothing happened. You all follow me? We did in chapter 2 or 3. Same thing. If this is reference 0 time is the time, the detonation time is 0, bang! Then shock wave, it takes a time to get to the ship, right? What happened to Hassan today?
I'm not sure about that. I haven't seen him for 2 days.
You haven't seen him for 2 days? Check it out. Maybe he's sick or something. You're a good friend to Hassan. Check it out. And what happened for nuclear submarine, nuclear explosion? This shape, wave shape, is different. Okay. And for the nuclear explosion is concerned, when nuclear explosion occurs in the air, ship is sitting there. Or let's say we are doing underwater explosion. Let's say, nuclear explosion occurs in the water, okay? In the water. Or free surface, relevant to, well, let's say underwater. Nuclear explosion occurs. And beginning would be like this. Beginning. But it doesn't come down. No. It stays there for a long time. Kill everything, then down. So that makes a big difference. It goes up there, then straight. When you have, this is explosive here, shock wave, nuclear explosion wave, for chemical explosion or conventional explosion, and it's like the shock wave front is like a paper thin, and a submarine could go like this, okay? As it passes by, this shock wave will just pass radial direction accordingly. But for nuclear explosion, a wave front is pretty thick. The whole boat could fall into that wave front, falling into that region and kill everything. Then just goes away. It's a different. However, what I'm claiming here is whether waveform is that triangle, or that kind of the wave, I can approximate if I solve the problem for waveform, I'm gonna put this. Does it bothering you? Oh, I'm gonna put the Z dot. Z dot is you have a ship here. It kicks vertically up. The baseline input excitation, I'm going to call the Z dot. Kickoff velocity. Kicks the ship. So, if I do this, then what's the reference velocity? When the reference velocity start, when the shock wave hit the target, then the ship start affecting by the shock, right? So I don't have to put this guy in there, right? But this is all up to you, right? Oh, I want to consider from the reference time is the detonation time, then I'm going to set that point equal to 0. It's up to you, right? Right? Yeah. All you have to do is whether you remember this equation, T minus T1 theta P max. You remember this equation set? So T1, what's a T1? What's a T1? R over C, right? What's R? Standoff distance. C is acoustic velocity in the water. Why use acoustic velocity, not the detonation velocity? The reason we are using acoustic velocity is our work is looking the target, not the immediate vicinity of explosion. When explosion charge is here, I am not talking about the target right next to it. I'm not talking about the target next to it. If it happened next to the target, what you have to do? You know? You have to go to church and pray hard. It's impossible to survive. DDG-67 USS Cole, when about 1,200 pound or about 300 or 400 kilogram C4 charge exploded right on the surface, small boat. It has a 40 feet long, about 12 meter long hole anyway. So we are always concerned about certain distance. What's the distance I mentioned to you as a rule of thumb? What's the distance? We are working on the survivability of the ship, some distance from the target. What's the distance? As a rule of thumb? 처럼. 연어.
Charge radius times 10.
Yeah. At least 10 times of charge radii. Doesn't matter whether this is a cylindrical charge, a spherical charge, you can convert always to the equivalent to spherical volume. Right? Then radius, then rule of thumb, at least about 10 times of the charge, distance away. Otherwise, it's a detonation problem, and the survivability is concerned to 0. The reason I'm saying is like a motivation and what we are dealing with for shipboard equipment. So here, so if we solve the shipboard equipment problem based on that sort of the triangular pulse, then if you know solution responds due to this kind of the input, then a lot of things you can compute by hand, or nowadays all that handphone has a calculator too, right? You can do that, all the calculation by yourself, without going through heavy computer code. So that's what I'm going to show you. Don't ever say in the field, I'm sorry, I don't have a big computer, so I cannot run LS-DYNA, I can't give you answer. Not productive. As an engineer, a lot of things, you can just put that in your handphone as a file or whatever, then you can compute right there. That's what I'm going to show you. To get your knowledge, you can do a lot of different things without having the computational instrument or computers, whatever. Okay. So now, subject to this, then what can I do? That's what the whole scope is. And as a final destination is this. Of course, for the nuclear situation is also special case of this triangular pulse response. If you say this, if this point is a T, if you pull this in a long time, this guy will move, eventually approach to the horizontal for that direction. So if you have a triangular pulse response, then you can do any kind of the wave response you can do. So that's what this chapter 7 does do that. But at the last section, I discussed about this. We have a lots of closed form solution. If excitation is a step function, this is called a step function. And of course, a triangular pulse, we have a general solution. A waveform could be all different kind. So as you look at the input excitation waveform, input excitation for shipboard equipment is always the base excitation. Because you mount the equipments with springs, which means some support structures, put it on the deck, or put that on the shell, you know, wherever excitation is coming from the bottom. Always a support here. So it's always base. For the equipment design, you have to worry about the base excitation. That's what the driving force to the shipboard equipment is. Then my question, this is like a base excitation. My question is, of course, this is let's call the VM. And this is just, say, just some value Vm. Rather than applying such a waveform, triangular waveform, I know the answer already. If the waveform input excitation is a step function, then my question is, rather than applying this triangle, if I apply this step function, whose response is already known, is it convenient? If this is this provide a conservative answer, is it very convenient? You know, out there in the field, if if I know the response due to step function, very convenient. Then if this is a conservative answer, then the triangular person. My question, is it conservative? What does it mean, conservative? Does it provide the response which is quite meaningful, but a little bit higher than the triangle? Then even if it's a little bit higher, economically maybe not that great, but still conservative, so it's quite acceptable as a preliminary design or initial design, then it's okay. So that's what we're gonna look at it. Rather than applying this, can I apply this? If it's good or not, that's what we're gonna discuss about. Okay, so I want you to read here this impulse loading or shock loading is a very short duration, high amplitude excitation. So it's so quick. All the damping mechanism is in deep sleep, and maximum response at early time occurs before the damping mechanism takes place. Bang! And the shock wave is gone. Then for the bubble, it comes like a half a second later, it comes in. Of course, at that time, all the damping mechanism in the system wake up, then contribute to reduce the response. Undamped response calculation will provide a good approximation for such a short duration, high amplitude excitation. And another good thing, I don't know whether it's a good thing or bad thing, you judge. Ship. Mast. It has a deck. All different deck. Of course, up here in superstructure, it has a deck. And here is explosion occurs right there. Then a shock wave comes. Then hit the hull. Hit the hull here. This is a shock wave. Shock wave. And I'm looking at the mast here, and all the antennas are mounting on the mast. So you have all different kind of antennas sitting here, or sometimes it's enclosed in the dome, but it's all there. Antennas is a chunk of mass. And when you have a high frequency shock wave, okay, when I say high frequency shock wave, it could go about maybe 1 kilohertz, where shock wave contains, it's a waveform is like this, pressure wave, hit it. This can contain 1 kilohertz easy, but this, as the shock wave passing through the ship is acting as a low-pass filter. Ship is acting as low pass filter. When you call, some of you did not take the course which I teach on spring semester. Consider it. I'm not insisting you must take it. My students, I need you, but other persons, it's up to you. Let's see. Low pass filter. Low pass filter is F, something like this, is F cutoff frequency. So all the ship system is acting as a low pass filter, throw away the high frequency component of the signature. Then by the time it, path could be all different, the path. Then by the time it could reach to the superstructure, all the high frequency components are gone. And as you look at this as main deck, where the superstructure built on it, and this will be in the vibration mode. Base excitation to the mast is low frequency vibration excitation, base excitation, no longer high frequency, because by the time it passes through the ship, all the high frequency components are mostly gone. And this mast, natural frequency usually are low frequency, something like a 20 hertz, 15 hertz, 25 hertz. 25 hertz is pretty high. So then base frequency may be very close to natural frequency of the mast, then they love each other, right? No? They love each other, right? Say yes. Hey, all the young men should say yes. Then they start to date. Then what happened? Then resonance occurs, right? Resonance, right? When you look at each other, there is a sparks. Whenever you meet each other, sparks, right? That's what the resonance is. Same. It's identical. Human analogy. Same as nature analogy. Resonance occurs. In small base excitation, the antennas are in resonance. Small base excitation, it really vibrate high. Then right at the time when the shock wave hit the ship, the antenna fly away. Have you seen that? Maybe search internet. In 1990, early 1990, there was a war in Middle East. Then I forgot the name of the ship, frigate, Bohoham. Antenna flew away. Naval officer happened to took a pictures that time. And low pass. So when you say shipboard equipment design and analysis is close to solving the vibration problem rather than shock problem, because shock has to have high frequency excitation, but mostly gone. by the time it passes up here. And also, it goes to the superstructure pretty fast. The wave speed is very high because steel, the wave speed is still very high, 25,000 feet per second. Acoustic wave in the water, about 5,000 feet per second. For the steel, very high. And instantly the wave hit it, the superstructure, hit the antennas, but high frequency components are all gone. So that's what you have to consider the rear situation. With this much knowledge, then you can start to look at chapter 7. That's what I'm going to look at chapter 7 together from Wednesday.